you might have. Actually, I just have a short question to the last presentation quickly, because yes, we also came across this problem of that that when you get data, it might be difficult to get even the raw data. You get already pre-processed data in sensors. But this is a technology that it develops very fast. So you might know what in sensors every year you have a new class, and also the algorithms in the sensors develop. Often they don't know you don't know exactly what they are doing. So we're working in the automotive industry in our project, and they don't tell us what they have. I mean, they tell us a little bit, but we cannot see the algorithms themselves. And so we can test the sensors, but then every year there's a new sensor, so we have to test again and again, and it's a difficult problem.
Yeah. Yuri's statement is not a question.
Yes, I agree. No, but how do you deal with this? So next year you have a new sensor, and every year you have to catch up with the sensor. So
yeah.
Okay, it was just a statement. So we leave the room for questions from the audience. So I have more questions if you don't want to ask, but real questions. Yeah, please.
Professor Cunha, in one of the examples, there was the variation of the damage parameter. I think it was a frequency, something like that, in the original and in several damage configuration. Now I don't remember which was the example, but there were something like 3 levels of damage.
4 scenarios of damage.
Or 4. Okay. And the dispersion of the data was higher in the damaged scenario, in the damaged state with respect to the reference one, which often occurs. The question is why? Why in the damaged scenarios the dispersion is higher? Because in both scenarios, if the variation is due to the temperature, the variation of the temperature should stay the same, but it always happens that, sorry.
Due to some, like time I could not explain with more detail, probably the application, what was done was following. So we, at Infant Bridge, we have data from several years. We noticed clearly the influence of temperature and intensity of traffic, and then we applied a multiple linear regression model to mitigate those effects. And afterwards, as we have not real damage on a new bridge, we used a numerical model of the bridge duly calibrated and validated based on the experimental measurements, and we have numerically simulated 4 different scenarios of damage with slight reductions of inertia in some sections in order to have some damage, but leading to very small variations of natural frequencies, not exceeding 0.2%. And then we have used 2 years of data. The first year was real data, and in the second year we affected the estimates of the second year with in correspondence with the percentile variations of natural frequencies provided by the numerical model. So the estimates of the second year are affected by damage, okay? Yeah. And then we built the control charts, and the control charts in the second year are able to flag the existence of that damage, okay? So it was a numerical procedure, but based on real data, to try to get confidence that this type of procedure is able to flag existence of significant structural changes in the structure. Okay.
Just a short question. Why did you simulate the Galileo signal instead of using GPS signal that is already available?
The meaning of my statement, probably there is a misunderstanding. I say that up to now, if we want to develop unit that will be working in 2020, we have not any possibility to test them. So we simulate that will be the information coming from Galileo in order to test the units. So it's a sort of, we have a delay in the industrial production of 4 years. So we were ready with the industry, the units, but the Galileo is not there. So there is a simulation that can help.
For Eleni, you talk about temperature, dealing with temperature effects on environmental conditions. Do you think that we should have this problem solved method by method, or in a completely decorrelated way with respect to the system identification methods or damage detection method you use?
I'm not sure I understood the question.
What I mean is, basically, should we have a solution to deal with the temperature effects corresponding to each method? Or
So I think an ideal scenario would be in the same way in which we now have operational model analysis methods that are widely applicable and are different. Some are in the time domain, some are in the frequency domain. We can also develop a toolkit of these types of methods that are also, let's say, in the same sense as readily applicable as stochastic subspace identification or frequency domain decomposition and so forth. So I think it's not, and it's not something, it's something that can be quite easy to do in the sense that these methods are quite developed at this point, but they're not really as well known, perhaps, and so they're not in the same degree adopted by the community and the and actually the operators. Let's say.
For example, you see, there are sensor work where basically they say we develop sensor robust to temperature or things like that. Mm-hmm. So the question would be: is the problem a problem of sensor or a problem of signal processing? I mean.
The effects of temperature, this is correct. They do affect the properties of the system. This is a given, but they also affect the measuring instrument. These are two different levels. So the two processes actually could be dedicated, but in fact, if one is just interested in a detector, then all of these effects are incorporated by these methods. And so for detection, you can devise an indicator that lets you know if you're in operational conditions or if something alarming is taking place already by incorporating these frameworks. Either since these are able to include the influence of effects either from sensor, let's say, influences because of temperature in this case, or also of because of the operational variation and its effect on the system. So the process of extracting the indicator is something that you can do. Either the effect comes from the sensor or from the structural response. This is what I mean.
I have a question to Professor Cunha, continuing one that was just asked. In your damage scenario analysis, you establish threshold values. You use this scenario analysis to establish threshold values for kind of early warning in case the damage occurs, which could be representative for the scenarios that has been analyzed. How do you deal with, this is done by numerical models, how do you deal with model uncertainty? How sensitive is this approach to model calibration, and what would be done in case you pass this threshold values that you have defined, so your model would need to be updated to account for the damage that has been experienced by the structure?
threshold values. That what we have done was to introduce numerically small damages, small enough so that we could be confident that the procedure could be able to detect in the future early damage. Our purpose was essentially to introduce damage associated to very, very small variations of natural frequencies, not exceeding 0.2%, as I said. And then we affected that second year estimates by percentual variations corresponding to those frequencies. And the building of control charts was able to flag the existence of something abnormal, yes? Of course, that in real applications we can have always the doubt when is it that variation serious enough to say, okay, we are crossing a threshold of an alarm level. That is probably more difficult to say in each application. And the feasibility of this also depends on the linearity of the behavior of the structural system that we are analyzing. And fortunately, we have begun with this application where the structure is very, very linear. And so it was amazing for us to obtain, after mitigation of the temperature effects, estimates in a very, very narrow range of frequencies of 5 millihertz only. But for instance, in another application at Forstua, concrete arch bridge, due to some nonlinear behavior associated to the expansion joints, the estimates cannot converge in such a narrow range of frequencies. And so we have always some difficulty to say when we have a threshold defining a safe situation from an unsafe situation.
I have a question to Bernd, because the title of your talk is called Reliability Updating. So, and I guess, ultimately you said that the monitoring does, in the case of the riser, is so cheap compared to the consequences that maybe in the ship it's a bit different, but did you actually calculate the reliability in this? Do you provide reliability estimates and say, okay, at that point you have to do something, or until that point you're okay? Or?
Yeah, no. Is this microphone?
You have to press me.
Yeah, no. As I mentioned, I think mainly the work is related to updating our model uncertainty, so you can reduce you can improve the precision of the calculation. So that means if you look at the probability of failure calculation, for sure you can reduce the probability of failure. So that is the main contribution, and that is both in the long-term and short-term sense. And of course, that also will reduce the expected cost because you have the risk because you have reduced probability of failure. So, but I guess there is more work to be done on this item in the future. So there's still quantifications that could be done because we did not formally put up a total model of the uncertainty of the, for example, soil stiffness, which is a significant contribution for the first example. So there is room for more work to really put numbers on the reduction of the risk, and of course the cost of the failure is a range of potential scenarios. You can have small leakage, you can have a loss of well control. So there are a range of possible consequences. So of course, this was not exhaustive analysis. There is still, for example, if this was to be looked into as a case study, there would be more work on quantifying the probability of failure and the amount of reduction of probability of failure.
But are these systems used in practice now? Is it academic or?
No, for the wellhead example, that's a big concern. In fact, there are a lot of publications by the oil companies on this topic. So That's really a serious concern because you have a lot of aging wellheads. You have to extend the lifetime of these wells. So that is a lot of work going on, and you have a number of studies performed on this item. And also even DNV, they have come out with a guideline on how to assess probability of failure for wellhead systems. With the ship monitoring, that's mainly at the moment research activities. You have the Finnish environment. They have a lot of experience from Baltic operations, and they have a ship, in fact, in the Antarctic, which is operated in collaboration with the University of South Africa. So it's called Agulhas, and that's a lot of measurements becoming available from that campaign. So that's also, but that's a larger ship than this Coast Guard. So it's a lot of ongoing work also on calibrating the prediction of ice load models, because the feeling is that the existing rules for ship design operating in ice, they are over-conservative. So that means you have two heavy ships, and the question is how much can you reduce the weight without having an increased probability of failure of the hull. And of course there's a limit. And if you have looked at damage to ship hulls due to ice loading, they can be very serious. You can have punctuation of the plates, you can have destruction of the frames, and in the worst case you can lose the ship. But of course pollution is maybe the most immediate consequence, and that is also a big fear in Arctic. If you have pollution in the Arctic, that's Shell just stopped operating in Alaska, for example, due to problems during towing of a drilling vessel, and they say Alaska no more. And of course the consequence for the oil companies and also shipping in Arctic is almost complete shutdown, at least for a while. So of course the consequence of failure also and pollution is quite serious. So there's a lot of work going on. We're also involved in university cooperation with Canada, Finland, Germany on Arctic research, and have a lot of PhDs looking at the total risk assessment for Arctic operations. That's a big concern, consequences of pollution and so on. Yeah.
Okay. Good. I mean, I guess the load model, I mean, when you model the load, to improve the load models, it's really a value of information that goes beyond the particular application. So that's for sure. Okay, so I'm looking at Juan, and I think we can allow one last question, if there is somebody who wants to ask a last question before lunch. I guess everybody is afraid that everybody else will be. Okay, so then we stop here, we go for lunch again, and we will come back at 2 o'clock. Thanks again to all speakers.
Yeah, it's a good question. Thank you.